Hi, welcome to a new video. Today we want to derive the predictive posterior for the Bernoulli distribution. For this, let us recall the posterior derivations for the Bernoulli model, and here we had a latent variable for the theta parameter, which we modeled as a beta distribution, and this distribution took two hyperparameters, an alpha and a beta, and it was affecting our dataset consisting of n weather observations, and they are later observed, therefore I shaded them. And of course they are modeled as the Bernoulli, and recall we found the posterior to be beta of an alpha prime and a beta prime, and the alpha prime and a beta prime are defined as follows. And this model is nice for assessing the quality or the probability of a certain theta parameter to appear. But it does not answer the question, for instance, if we observe the weather a couple of times, what is probability that the next day will be a good day? And that's where the predictive posterior comes in. For this, let us start with the graphical model, and I will take most of the parts from the original graphical model. Okay, again, we have a latent theta parameter, which takes an alpha hyperparameter and a beta hyperparameter. And this theta is affecting the WI samples, so the weather that we observe. And we observe n samples, this is again our data set. And now, different to before, we also have another random variable, and that's t, and t is tomorrow's weather. So t is tomorrow's weather. And we want to say something about tomorrow's weather. And t is, in our case, also a Bernoulli distribution, since we keep our model, and it's distributed with the same theta that is also latent. But now we can use our posterior information in order to be more informed, or our posterior on the theta, to be more informed on what kind of a weather it will be tomorrow. For this, let us write down the joint distribution. And the joint is a probability of theta, then the dataset, and tomorrow's weather. And according to the rules of factorization, we have a p of theta times a p of d given theta times a p of t given theta. Okay, and now let us go on. So actually what we want is, so maybe to write this down to make this clear, we want a p of t given d. So we want to have a probability of t based on our observations of the data set. So maybe we have to now do some manipulations here. Okay, first up, let us split this distribution according to the chain rule of probabilities, and therefore we get p of theta and d given t p of theta and t given d times p of d is p of theta times p of d given theta times p of t given theta. And now let us divide by p of d, so the probability of the data set, and then we have p of theta and t given d is p of theta times p of the dataset given theta divided by p of the dataset and times p of t given theta. And I already put this in a format that you might already see Bayes' rule here. So this is Bayes' rule, and it equals p of theta given d. And nice, that is our posterior. So let's note this down. This is our posterior. Excellent. Okay, let's replace it so that we have p of theta and t given a data set is the posterior, p of theta given a data set, times p of t given theta. Okay, and now let's go back. What we actually want is p of t given d, and we have a probability where this is in, and we can get this out by marginalization. So we can marginalize over theta. And this works as following. We get a p of t given d as the integral, and we have to integrate because theta was a continuous random variable, takes values between, so let's write this down, theta is continuous and theta is from 0 to 1. And we have to integrate over our recently found distribution over all thetas. Okay, let's plug this in. Then we take what we have here. This is over theta of p of theta given d times p of t given theta d theta. Let's put in the limits of our integration. Theta goes from 0 to 1. And p of theta given d, this was our posterior, which was the beta distribution with alpha prime and beta prime. And we multiply this with a Bernoulli with theta, d theta. And let's plug this again, and I will make this even more concise. And beta is 1 over the beta function of alpha prime and beta prime times theta to the alpha prime minus 1 times 1 minus theta to the beta prime minus 1 times theta to the, and t is our random variable, times 1 minus theta to the t minus 1. No, sorry, the 1 minus t. Okay, d theta. And now we have something that is complicated, and I wanted to bring this up and maybe let you think about how you would potentially solve such kind of integral. And the thing is, this integral is difficult. And before I provide you with the solution, I want to show something that is really common in finding the predictive posterior. And what we actually have here in this very line is an expectation. So this is an expectation over theta distributed according to p of theta given d, so distributed according to our found posterior, over p of t given theta. And this particular expectation is can be evaluated with sampling. So can be evaluated with sampling. And that's typically done if we have problems where these integrals become intractable. So if integral is intractable. Okay, but for this particular case, there is an analytic solution, so we are lucky. And the analytic solution is given as follows, as the alpha prime to the power of t times beta prime to the power of t minus 1 over alpha prime plus beta prime. And if we now, for example, assume that, let me think. No, it should be 1 minus t. Okay, let's take a closer look at what we have. So this was our predictive posterior. So it was the probability of the next day's weather given our weather observations. And we can look at two examples. So the next weather can either be good or bad. And so we can ask us, what is the probability that the next weather is good? So it is 1. And then we have alpha prime to the power of 1 times beta prime to the 1 minus 1 over alpha prime plus beta prime. 1 minus 1 is 0, so beta prime to the 0 is 1. So we have an alpha prime over an alpha prime plus a beta prime. And equally, we will find the case for bad weather. And for this, we have the beta prime over the alpha prime and the beta prime. And if you recall, the alpha prime was nothing else than our alpha plus the sum of all our observations. So in essence, what we're doing here is we have some sort of a predictive posterior based on our actual counts, so our actual times of good weather, and of our pseudo times of good weather. And these pseudo times, they incorporate the idea of us knowing about like the previous state of the weather or how likely it is, since we're probably in a region where it is more likely to be of a good percentage or a high percentage. And this is how we can use a predictive posterior in order to find the probability that the next day is going to be good. Thank you for watching this video.